Okay, go ahead and get started. I'm going to give you a little bit of what my plan is for today. So essentially, I want to cover like 3 big sections of what is constituting the material on the second prelim, and those 3 sections, which I feel like are relatively disjoint and separated, are first relations, the second finite automata, and the third is combinatorics. The way I'm going to cover them, I'm going to target specifically the topics that were tested or touched upon inside the practice exam. As you probably by now know from Prelim 1, the practice exams that Matt and Noah release on Canvas are very, very good representations of what you have to do on the real exam. And so although there is other topics or other skills, other types of problems that will fall under the category of, say, like relations and automata and combinatorics, I'm going to specifically target the ones that seem to like really appear on the practice exams so that you will be best prepared for the real exam. All right, and I'm planning on basically doing this in like 3 very separate sections. And between each section, we'll probably just take like a short few-minute break, just so that like we're not like doing this for too long. All right, are there any questions? Anything that you guys want to talk about, mention? Yeah.
I don't fully understand that.
Okay. I mean, looking at the practice exam, there doesn't seem to be any like diagonalized, like there doesn't seem to be like problems which make you actually do a diagonalization proof. So I'm going off of what the practice exam looks like. So like I haven't actually seen the real exam, but if my assumption is correct that the practice exam looks a lot like the real exam, so if my assumption is correct, then I feel like it's kind of unlikely that you will have to construct a diagonalization proof. Yeah.
Can you like go over strategies to write like proofs regarding like anti-symmetry or?
Yes, I will. I have prepared at least one example by which to do these things. Yeah. Any other questions? Okay. All right. So I want to get started with the first part of the review session, which will be on binary relations. And so before I even start on and jump into maybe the deep concepts of a relation, I want to like give you sort of the base, the foundation for how relations work. And from that, we're going to build up from this foundation into the various properties, reflexivity, symmetry, transitivity, and also go into examples of like how to prove such properties. So a relation, in effect, you can think of a relation as like comparing objects together. So this is not formal at all, but in a very intuitive sense, you can think about relations as a way of comparing objects together. And it's difficult for me to find the right English words to convey precisely to you the mathematical definition of a relation. But I want to like at least give you some intuition that the relation is comparing 2 things, like comparing different objects with each other. And whenever we're comparing different objects with each other, we need to talk about what objects we are comparing. And so therefore, whenever we have a relation, there's always an underlying, there's at least one underlying set. And so I'm going to first give you the most general case, which is that we are comparing, I put this in air quotes because it doesn't quite capture all the nuance of what a relation is, but we're comparing elements of set X with set Y. And so what this means is that we are going to take an element inside set X, and we are going to talk about like how it compares with an element inside set Y. And so here, this definition of saying comparing, or I wouldn't even say a definition, this intuition of saying comparing elements of set X with set Y, we can intuitively at least call this is like a relation on X and Y. And so for example, let me give you, say, like, let's say the set X is 3 numbers, and the set Y are 3 letters, A, B, and C. And I want to say, like, one, let me write it in this way, like 1 R A. And now this is the next part of the idea of comparing. And I want to maybe even qualify the word comparing that I'm using here, because I think a relation isn't quite just a compare. Oh, let me fix this, because let me mirror the video in the Zoom so that it's not backwards. Oh, and there's a question in the chat, which is whether or not we can ask questions. Unfortunately, at least on Zoom, I don't have like someone monitoring the Zoom. So it's going to be hard for me to monitor the chat frequently. And so I guess for people on Zoom, if you have a question, it would probably be best to just unmute, and so that we can hear it through the speakers. Okay. So maybe I'm going to even qualify what I maybe want to change this word comparing. And I want to even say and to make it even more general, to say that it's relating elements of set X with set Y. Now, in the context of a relation, there's often the notion of comparison. And later on, we'll see that, like an equivalence relation, a partial order, effectively, intuitively are comparing. But for the sake of like the most general situation of a relation is just, quote unquote, relating elements of set X with set Y. And so when I'm going to write something like this 1 RA, and what this intuitively means is, say, like 1 is related to A. Now, the English word related doesn't quite capture all of the nuance inside what a relation is. Namely that normally when we say the word related, if I say 1 is related to A, you would automatically were to think that, say, like A is related to 1, right? If you had 2 people and you said these 2 people are related, it doesn't matter whether you say like person X is related to person Y or person Y is related to person X. In effect, those 2 statements are the same. However, in a mathematical sense, this relation, this word relating, moves in one direction. So this is like, maybe I need to put this here, a one-way relating of the elements of set X with set Y. Therefore, if I were to write, say, 1 is related to A, I'm unable to write A is related to 1. I'm unable to write something like this, because specifically when I'm relating set X with set Y, I'm saying things in set X are related to things in set Y. And therefore, I cannot reverse the direction here and say this thing in set Y is related to something in set X. I want to now define a little bit more formally what this notion of being related is. And so a relation R is most formally a set of ordered pairs, X, Y. It's a set of ordered pairs where X, this comes from our set X, Y, this comes from our set Y. And I don't want to write set builder notation, because the set builder notation would imply you could have every single possible pair of X and X, Y, and Y. So instead, I'm going to write it maybe like this. A relation is in effect a subset of X cross Y. What is R? R is a set of ordered pairs. R is a set of ordered pairs where this little x comes from the set big X, and this little y comes from the set big Y. And I'm gonna, just to make this really clear, this is not necessarily all such ordered pairs. What I mean by this is, if one is related to A, this is the same thing as the ordered pair 1A. I'll put it right here. This is the same thing as saying the ordered pair 1A is inside relation R. And how do I understand this? R is a set. That set contains ordered pairs. What are those ordered pairs? They're every single ordered pair where the first thing is related to the second thing. Therefore, if R is a relation, it's a set of ordered pairs. If I know that 1 is related to A, I know that the ordered pair 1A is an element inside this set of ordered pairs. I'd like to make this a little bit more concrete. And let's say that here, let me give you an example of a relation between X and Y. So here I can give you an example. Let's say I have 1A, 2B, 3C. This is, let's say this is now my R. In this, I know that 1 is related to A, 2 is related to B, 3 is related to C, but I know that 1 is not related to B. I want to present this formalism to you so that you have this idea in your mind, but a lot of times the most convenient way to think about it is to think about it like this: 1RA or 2RB or 3RC, particularly because I may have made a slight error in starting with the fact that the relations only are comparing two elements together. Relations are most generally simply, quote unquote, relating elements together, but they are so often used for comparison that it's helpful to think about it like this. Because if you think about how you compare, say, two natural numbers together, you would say like 1 is less than 2, 3 is less than 5. And so in effect, that relation kind of sits in the middle of things. And also like reads more clearly, 1 is related to A, 2 is related to B, 3 is related to C. And so I'm going to primarily use this kind of notation and almost not touch this set and ordered pair notation, except I just want to present this formalism underneath so that you have this idea of what relation really actually is like underneath. All right. So I want to now say, I now want to focus on a specific, a very commonly used type of relation. A relation most generally can relate things between two different sets. And however, a lot of times when you're doing relations, you're actually relating things between the same set. For example, if I had a group of people and I have a relation, someone is the parent of someone else, is the parent of is my relation. Then let's say you have a group of people and you can say like, person X is the parent of person Y, or person Y is the parent of person Z. Now, you could do a relation between two different sets. You could have like a group of kids and a group of parents, and then you say like, this person is, or a group of parents and a group of kids, and you could say like, this is the parent of this is the parent of this. But alternatively, you can think of it as like a whole group of like a bunch of people. And if your relation is like, person X is the parent of person Y, then you would say like, essentially, the pair XY is inside your relation. Or you could say like, person X is related to person Y. And what does it mean to be related to? Like, is the parent of person X is the parent of person Y. I chose this example to emphasize to you the kind of asymmetry, the fact that X being related to Y is not the same thing as Y being related to X. If person X is the parent of person Y, that is very different from saying person Y is the parent of person X. I want to now really focus our attention on, so I want to give you this in terms of its most general sense, but I want to now focus our attention on what it means to be a relation on set X. And a relation on set X is in effect the same thing as a relation on set X with set Y. It's just that now I'm relating elements inside the same set. In other words, as to the example over there, my X here and my Y would have to be the same as my X. And so what would a relation look like here in terms of this ordered pair formalism? This relation here would be a set of ordered pairs. Let's say, let me use this as A, B. And A would be from, this would be from X. And B would also be from X. And in effect, if I were to say, and if I were to give you an example here, I could make a relation here, which is say like 1, 1, 2, 1, 3, 2. And here, I'd say 1 is related to 1, 2 is related to 1, 3 is related to 2. Are there any questions so far about the formalism? I wouldn't worry too much about this, but I just want to put it here so that it would set the foundation for the rest of what we are going to do. All right. I want to focus particular attention on special cases of relations. And so I'm going to almost exclusively focus our attention on this relation on set X thing. Forget, I presented this in order to give you the full general sense of a relation, even between two different sets. But in the following discussion, I'm going to almost exclusively focus on relating elements, not between two different sets, set X and set Y, but relating elements between the same set X with set X. And so therefore, from here on out, basically all the examples that I'm going to give you and basically all that we're going to talk about is on this kind of aspect, a relation on set X where we're relating elements inside the same set. And by relating elements inside the same set, that's no different from this very general sense of X and Y. It's simply that Y set is just the same as my X set. So I'm not going to have two different, so in the following discussion, I'm going to stop having two different sets. And I'm just going to talk about a relation on set X and a relation on set X comparing elements within the same set. If you remember in functions, we place very little restrictions on sort of what is going on inside the codomain. In other words, as long as we had a domain, and as long as there was exactly one arrow coming out of each element inside the domain, really, for a function, we really just almost didn't care what was happening inside the codomain. And when we started to care about what was happening inside the codomain was enforced by things like injectivity and surjectivity and bijectivity, namely like at least one arrow is pointing to an element in the codomain, at most one arrow is pointing to the element in a codomain, and things like that. We have a similar setup for relations. Notice here, in the way that I've just presented to you what a relation is, I've given relations to you in a very, very general sense. In effect, a relation is simply a set of ordered pairs. And these ordered pairs, the first thing has to come from my set X, second thing has to come from my set Y, or in the case of, in the special case of a relation on set X, a relation is simply a set of a bunch of ordered pairs. And what are those ordered pairs? I have one thing inside set X, another thing inside set X to say that this thing is related to this thing. And so like here, this relation on set X from the set, the underlying set of 1, 2, 3, I gave one example here of a relation, but I could have come up with any sort of set of ordered pairs where every element inside the set, the first one is from set X, the second one is from set X, and those would all be valid relations. For example, the empty set is a valid relation. I could have had a set containing only, I could have had a set only containing the ordered pair 1, 1. I could have had a set only containing the ordered pair 2, 2. I could have had a set only containing the ordered pair, say 3, 3. And all of those things would be valid relations. So notice here, when I make this set of, when I think about the kind of options that I have for valid relations, I have numerous options for valid relations. All I need is a set containing some ordered pairs. And those ordered pairs just need first element from set X, second element from set X. And then I have a relation. Now, just like in functions, there are also other terms which provide special restrictions on what a relation, on the types of relations. And so these special terms I'm going to give are the properties of being reflexive, symmetric, anti-symmetric, and transitive. For each one, I'm going to provide you with a definition, and I'm also going to provide you with an example coming from relations on our set X. So I'm going to write over here, our set X is, write the definition here. So here's an example. Here's the definition. And the examples, these are our relations on my set X containing elements 1, 2, and 3. What is the definition of reflexive? For all X inside X, I'm going to use X here as that kind of underlying set of what we are comparing. I don't want to say comparing, or relating. For all elements inside, so just as a reminder, what's X? X is, as I have probably spent like quite a bit of time explaining before, what is X? X is this underlying set of the objects that we are relating. For example, so here I'm focusing exclusively on the special case relations on set X. X is what are the things that I am trying to relate to each other. In this case, in this example, the X was the set containing 1, 2, and 3. I'm trying to relate together, the elements 1, 2, and 3. Here, I'm going to also give other examples relating together elements inside the set 1, 2, and 3. What are the elements I'm relating? That's my set X. For every element inside set X, little x, is related to X. So a reflexive relation R, so R is my relation. A reflexive relation R is that for every element inside the set of things that I'm comparing, X is related to X. I'll give you an example here of a relation. 1, 1, 2, 2, 3, 3. For every element inside the set of things that I'm comparing, let's say 1 is 1 related to 1. Yes, because the ordered pair 1, 1 is inside my relation. How about for 2? It's also 2. This is satisfied because 2, 2. 2 R2. 2 is related to 2 because this ordered pair 2, 2 is inside my relation. So how about 3? 3 R3 is true because the ordered pair 3, 3 is inside my relation. But a non-example would be if I had the 1, 1, 2, 2. This would not be reflexive because the element 3, for it to be reflexive, I need every element inside my set X to satisfy X is related to X. But here in this example, the element 3 is not related to 3. 3 is not related to 3 because the ordered pair 3, 3 is not inside R. So therefore, to show that something is not reflexive, we need to give, say, like an ordered pair where both of these are the same and they're not inside the relation. Symmetric for all x, y inside set X. X ry implies y rx. Symmetric is basically the special case that is now the special case that I've made a long explanation to kind of clarify that a relation in general is one way, but when a relation is symmetric, we get that kind of two-way relationship. The example, I'm going to give an example here, which is say 1, 2, 2, 1. If 1 is related to 2, then 2 is related to 1. I want to mention here, it's not an issue. It's not a problem. It's not an issue that say like 1, 3 is not inside the relation. all the symmetric property requires is that if x is related to y, then I need y is related to x. If x is not related to y, if you remember for an implication, if x is not related to y, if this is false, this implication automatically becomes true. So if x is not related to y, I have now no restrictions. Like this implication automatically becomes vacuously true if x is not related to y. And so I'm only required to consider in the case when x is related to y, do I also have y is related to x? So the fact that, say, something like 1, 3 is not inside this relation does not make it not symmetric. This relation is symmetric because 1, 2 is inside the relation and 2, 1 is inside the relation. But if 1, 3 is not inside the relation, it doesn't really matter. The only thing that I'm worried about is that when I know that, say, something x, y is inside the relation, I also need to make sure that its reverse is also inside the relation. If 1, 3 is not inside the relation, I don't need to make sure that, say, 3, 1 is inside or not inside the relation. All I need to consider is when x, y is inside the relation, I also guarantee y, x is inside. A non-example would just be the set 1 containing one ordered pair 1, 3. Why is this not symmetric? It's because this violates this if statement. If 1, 3 is inside the relation, I would need 3, 1 to be inside the relation, but here 3, 1 is not inside my relation. Anti-symmetric for all x, y inside x, x are y, and y are x. This implies x is equal to y. I want to give you a fairly silly example. The empty relation is anti-symmetric. Why is it anti-symmetric? Because as in the case of symmetric, I only need to worry about if x are y and y are x is inside my relation. Then I need to check x is equal to y. If this antecedent is false, sort of like all bets are off. This implication automatically goes through. And so in the case of the empty relation, when do I ever have x are y and y are x? Never. Therefore, this antecedent is always false, and so its implication is always true. I'm going to give you maybe a less silly example here. How about 1, 1, 1, 2, 1, 3. 2, 2, 2, 3, 3, 3. If x are y and y are x, then x is equal to y. Let's look at let's first think about the 1, 2. Let's first think about, say, 1, 2. If x are y, how about y are x? 2, 1. Well, 2, 1 is not inside this relation. Therefore, antecedent is false, and so this implication is true. When do I really start to like get into the danger zone of like x are y and y are x that I need to check x equals y? You don't need to check for 1, 2 because like 2, 1 is not inside the relation. 1, 2 is inside the relation, but 2, 1 is not. So this implication automatically becomes true. When do I actually have both of these become true? Well, it's only when I have 1, 1, 2, 2, and 3, 3. 1, 1 is inside the relation, and I flip it around. 1, 1 is also inside the relation, and 1 is equal to 1. Here, let me give, I think, is a non-example. This here is a non-example, and if you were, and just to remind you, how do I create such non-examples? I'm looking for something where x are y and y are x, but x is not equal to y. If you remember, to create a non-example for an if statement, you want to make sure the antecedent is true, but the conclusion is false. To bring this even back one step further, what is this definition actually? It's a for all statement with this property. And so if something is not anti-symmetric, if I were to negate this for all statement, what would I do? I would bring the negation inside and would flip this for all to a there exists. I'm going to give you a little more intuitive way of thinking about that, which is if I don't want it to be the case that every xy satisfies this property, how do I show that that's not true? All I need to show you is one example where one example of an xy which doesn't satisfy this property. If this property says that every xy satisfies this, to prove it false, all I need is one example of an x and y where this property doesn't hold, then therefore it doesn't hold for every xy. So to create this non-example, all I did was I tried to think about one example of an xy where this would be true, this would be false. And so in this relation, that is the case because 1, 2 is inside my relation. The flip side, 2, 1 is inside my relation, but 1 is not equal to 2. Right? For transitive, for all x, y, and z inside the set of things that I am relating, if x are y and y are z, that implies x are z. I want to give you an example here. How about the relation 1, 2, 2, 3, 1, 3. If 1, 2, if x are y and y are z, then I know that x are z. Let's look at this. 1, 2 1 is related to 2. 2 is related to 3. 1 is related to 3. How about the case, like, what about like 1, 2, 2, 1? Like, how come I only checked 1, 2, and 2, 3? Well, recall that this if statement requires x r y and y r z before I can include x r z. Here, 2, 1 is not even in, so for the case of x equals 1, y equals 2, and z equals 1, I didn't have to check this case because 2, 1 wasn't even in my relation. The y r z, the 2, 2, 1, wasn't even inside my relation. And so therefore this antecedent is false. This whole thing, this if statement still remains true. So as a reminder from the first part of the course on propositional logic, when do I really have to check this whole like transitivity, like or transitivity, symmetric, asymmetric, anti-symmetric? Like when do I have to check all of these things? I really have to check whether or not this is satisfied when these things are true. I really have to check when the conclusion is satisfied, when the kind of antecedent part is true. If the antecedent is false, I don't need to check it, because if the antecedent is false, this if statement still remains true no matter what. The only things I need to check are when the antecedent is true. Is it always that when the antecedent is true, that the conclusion is also true? Here, I also want to give you a non-example. Just say 1, 2, 2, 3. Right, in this case, 1 are 2, 1 is related to 2, 2 is related to 3, but 1, 3 is not inside the relation, 1 is not related to 3. Right, I want to now give you I want to present a few more definitions. The first is that of an equivalence relation. An equivalence relation is simply a relation that is reflexive, symmetric, and transitive. And the second definition I want to give you is that of a partial order, which is it has to be reflexive, anti-symmetric, and transitive. So a relation, if it were reflexive, doesn't have to be symmetric, doesn't have to be anti-symmetric, doesn't have to be transitive. So sort of a relation, just like a function, it can be individually injective, individually surjective, or both. Similarly here in a relation, when do I have a relation which is called an equivalence relation? It's when my relation satisfies three properties: reflexive, symmetric, transitive. When is my relation a partial order? It's when it satisfies three properties: reflexive, anti-symmetric, transitive. All right. And to give you a little bit of intuition behind, say, an equivalence relation, partial order, this is sort of generalizing, a generalized version of what it means to be equal. And this is a generalized version of what it means to, say, be less than or equal to or greater than or equal to. I'm going to show two examples of relations and also the proofs, the methods of doing proofs for those relations. But I want to, in those examples, I'm going to show you a little bit of the kind of intuitive dangers of really thinking about this as equals and really thinking about this as less than or equal to or greater than or equals to. But it often helps to sort of be like, when you're like thinking about it intuitively, to think about it as these kinds of things. But I want to just caution you not to take this analogy of equals, less than or equal to, greater than or equal to too far. And it's probably not super clear right now what I mean by let's not take this analogy too far, but I hope that in the following, I'm going to show you a few examples, and I hope that that will clear things up about this. All right, example one. We're going to have a relation. My relation is going to be, I'm going to have a relation on Cartesian product of the naturals with the naturals. What do these elements look like? These are ordered pairs where this one is a natural number. This one is a natural number. I want to warn you of an important difference. These ordered pairs are the objects that we are comparing. This is not to say that this natural number is related to this natural number. Remember, I'm saying I have a relation on n squared. What does that mean? That means what are the things that I am comparing? I am comparing objects inside this set. And what do objects inside the set look like? They're ordered pairs, a natural here, a natural here. I want to give you so what relation am I using here? This is a relation. I'm going to use a symbol. I'm going to stick with a symbol of like A, R, B. I'm going to have one object, x0, y0. x0, y0 is related to x1, y1 if there exists an m such that x0 minus x1 is equal to 5m. There exists an n such that y0 minus y1 is equal to 7n. And to be more specific, this m needs to be in the integers. This n needs to be inside the integers. I want to give you an intuitive idea of what this is. This is that this ordered pair is related to this ordered pair. If these two differ by a multiple of 5, these two differ by a multiple of 7. Therefore, I can say that let's say 2, 3 is related to 5, 10. No, 7, 10. These two differ by a multiple of 5. These two differ by a multiple of 7. How would I write this in that old formalism of like ordered pairs? I would say the ordered pair 2, 3, 7, 10 is inside my relation R. I hope this makes it clear the distinction between the two types of ordered pairs here. This first ordered pair 2, 3, we are not comparing 2 with 3. What are we comparing? We're comparing elements inside n squared. What do the elements inside n squared look like? They're ordered pairs of two natural numbers. So 2, 3 is an object that we are comparing with what other object? 7, 10. This is an object that we are comparing or relating with this object. We're relating these two objects together. I'm saying 2, 3 is related to 7, 10. And to convert it into the ordered pair format, I say this thing, remember x, r, y. Remember the x, r, y is the same thing as x, y. The ordered pair x, y is inside R. So this thing is related to this thing. Therefore, the ordered pair of this thing is inside R. This outer ordered pair is for the relation. This inner ordered pair is just the like type of elements we are comparing. I keep saying comparing because I keep talking about like equivalence relations and partial order, but just to be more general, I'll say relating. This outer ordered pair is the ordered pair for the relation. This inner ordered pair is simply a fact that we are doing a relation on n squared. And so what do the objects that we are relating look like? They're ordered pairs of two natural numbers. If I were to do a relation on n cubed, I could have, say, like 2, 3, 4, 7, 10, 11, or something like that. This outer ordered pair has to have two elements because I'm relating two things together. The inside thing here can be whatever you want. It could be like cat, octopus, or something like that. As long as this thing's inside the set of things that I'm relating together. So now I want to do the various proofs for relation proofs or counterexamples for reflexive, symmetric, anti-symmetric, and transitive. Let's start with reflexive. As has been the case before in doing function proofs, we're going to resort to the rules of how do you prove, say, a for all statement? How do you prove a imply statement? How do you do, we're going to resort back to these kind of, how do you prove or use various logical propositions? The proof for reflexive, what kind of a statement is reflexive? What kind of a statement is reflexive? Does anyone want to, what kind of, is it a for all statement and implies that, it's a for all statement. First thing I write to prove a for all statement, I take an arbitrary I know for people on Zoom, the definitions are not visible. So I'm just going to quickly rewrite it right here so that you can still reference them for all x, 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 r, x. To prove this, take an arbitrary x inside x. Well, what's my set x? What are the things that I'm comparing, relating, elements that we are relating? In this case, that's n squared. So for all x as an element inside n squared. So how am I going to start this proof? How am I going to prove this for all statement? How am I going to prove this for all statement? I'm going to take an arbitrary element. Let me call it x inside what set? n squared. And what do I have to show about this element x? I need to show here that x is related to x. Is this bottom part visible? Or I can probably move the board up a bit. This work better? Okay. The same techniques as we have been doing in the past. I'm going to show you how the techniques of, say, how do I prove a for all statement, working top, bottom, and doing all of these things are going to apply very, very well for these proofs. Yeah. Mm-hmm.
You said for all x and the bigger x?
Yes.
Isn't the bigger x is a subset of n squared and then the little x is a subset of x?
No.
You take an arbitrary element x and the subset of n squared.
Oh, so the big X is simply the elements, the set of elements that we are comparing with each other. What things are we comparing with each other? In this case, we're comparing together ordered pairs of natural numbers. This little x is an element inside my big X set. What do my elements inside the set look like? They're ordered pairs of natural numbers. So I'm going to here give you a very, on the first prelim, I think one thing that would have helped a lot of people to be able to work out the proofs is to do this technique of working from the top down and also the bottom up. I strongly advise doing this because if you don't do it, you are still going to do it in your head. And so you either write it down or you do it inside your head. And so you might as well just write it down so that you don't have to keep all of this stuff inside your head. And so I strongly advise doing this technique of working from the top down and the bottom up. And so I'm going to, rather than give an abstract explanation, I'm going to just use these examples to like maybe hammer home like this concept of using the top down, bottom up strategy. Reflexive. For all x inside x, I'm going to prove x r x, little x r little x. So to prove this for all statement, take an arbitrary element x inside n squared. And I'm going to prove that this little x is related to little x. What does it mean for little x to be related to little x? Well, it means that my x has to, well, this might be a little hard because my definition requires to look at x in terms of this form. So even before I do this, it would be really helpful because my definition incorporates x as an ordered pair. So it'd be really helpful to be able to work with the individual components of this ordered pair individually. So if I take an arbitrary element x inside n squared, I'm just going to say let x equals to this ordered pair. That way I can like talk about the individual components of this little x without I can just reference x0 and y0 very conveniently as the individual components of this little x. Now x equal to this. Now, if x looks like this, what does it mean for x r x? It means, what does it mean for x0, y0 to be related to the same thing, x0, y0? It means there exists an m in the integers. So maybe even before I write this, what does it mean for x to be related to x? Well, it means that, well, what's x? Well, x looks like this. So that would be the same thing as saying x0, y0 is related to x0, y0. What's this? How do I prove that x0, y0 is related to x0, y0? I work backwards again. I use the definition. So I simplify. So what's my goal? My goal is xrx. I sort of give myself a little more to work with. What does xrx mean? It means x0, y0 is related to x0, y0. And how do I bring this? I'm slowly doing this unwrapping again. I'm unwrapping things in terms of definitions and logic. I want to rewrite this in terms of its definition. There exists m such that x0 minus x0 equals 5m, and also that there exists n such that y0 minus y0 equals to 5n. This is what I want to prove. Now notice what this goal is. This is now my new goal. What kind of a statement is this? It's an and statement. So I have to prove this thing, and I have to prove this thing. How do I prove this? I'm going to prove their exist statement. How do I prove their exist statement? I give an example, and I show that it satisfies the required property. In this case, it should be pretty easy. M equals 0. M equals 0, does that satisfy the required property? Well, what's x0 minus x0? That's equal to 0, which is equal to 5 times 0. How about this? N equals 0, that works. What's y0 minus y0? That's equal to 0, which is equal to 5 times 0. Therefore, this m satisfies this required property, and so there exists this m that satisfies this. This n satisfies the required property. Therefore, there exists this n that satisfies this. I don't want to dwell on this too much because because I think it will be clearer if we just keep going with more and more of these proofs. So how about let's do symmetric? Yes. Mm-hmm.
7n or 5n?
Wait, sorry?
Do you mean 7n? Like one?
Oh, yes, 7n. Yeah, thanks for catching that. Symmetric, I remind you of the definition for all x, y inside R. Inside x. X, R, y implies y, R, x. What is this? This is a for all statement. What do I write? Take an arbitrary x, y inside. What's x? What are the things that I'm comparing? Order pairs of naturals. What do I want to prove? X, R, y implies y, R, x. What type of a statement is this? Is it an implied statement? How do I prove an implied statement? I assume this, I conclude this, assume X, R, Y. Oh, and before that, whenever the objects that I have, X and Y inside n squared, are these kind of like composite objects with like ordered pairs, it always helps to just write out what these objects look like. So I'm again going to say let x equals to x0, y0, y equals to x1, y1. That way I can just reference the individual components very, very conveniently. So it always helps when you have a relation on something like weird, like this n squared that contains like, numerous like subcomponents, that when you take the arbitrary xy, just write out new variables that represent the individual subcomponents inside x, the individual subcomponents inside y, and that way I can reference them very quickly. Assume x is related to, and so back to here, how do I prove this implies? I assume this, I conclude this. So I want to assume x, r, y, and get down to y, r, x. Again, how do I keep going with this? I want to use definitions and logic to kind of unwrap more of stuff I know, stuff I want to show. What's x, r, y? That means that there exists this m. Let me call this an m1, such that x0 minus x1 is equal to 5 times m1. And also there exists this n1, such that y0 n1. What do I want to show? I want to show that there exists some integer, let me say m2, to distinguish it from this m1. I know this m1 exists, but I want to see if there's also an m2 such that y-r-x, let me make sure and what's y-r-x? So here I'm subtracting x0 minus x1, but here I've reversed the roles y-r-x, and so I have to go x1 minus x0 equals to 5m2. Similarly, there exists an N2 such that y1 minus y0 equals to 7 and 2. So this is the stuff I already know. I've assumed x or y. I get this from the definition. I want to prove y r x. This is the definition of y r x. Notice I've chosen variables m1 and n1 here. This is the stuff I know. But this stuff that I want to show m2 and n2 is not necessarily the same as m1 and n1. And therefore, I've chosen different variables to distinguish. This is the want to show stuff. This is the stuff I already know. How do I fill in this gap? Again, this thing here, this whole thing here is an and statement. So I want to prove this, and I want to prove this. So what's the m2 where x1 minus x0 is equal to 5m2? Well, I know x0 minus x1 equals 5m1. So I can say set m1, set m2. So again, I want to remind you, how do I prove a there exists statement? So here I'm proving an and statement. So I technically have proof number 1, proof number 2. Here I'm going to do proof number 1. Here I'm going to do proof number 2. How am I going to do proof number 1? Well, what's statement number 1? It's a there exists statement. How do I prove a there exists statement? Give an example, show that it works. What's my example here? M2 is negative M1. Let me show you that it works. What's x1 minus x0? Well, this is equal to negative of x0 minus x1. What's x0 minus x1? It's 5m1, so this is negative 5m1. And this is equal to 5 times negative m1. What's negative m1? It's m2, 5m2. The second part is completely analogous. I say set n2 equals to negative n1. So what's statement number 2? It's a there exists statement. How do I prove a there exists statement? I give an example, show that it works. What's y1 minus y0? Well, it's negative of y0 minus y1. What's y0 minus y1? It's 7n1. So this is negative of 7n1. It's 7 times negative n1. What's negative n1? It's n2, 7, n2. Therefore, y1 minus y0 equals 7, n2. I want to warn you of something that is a very common pitfall in exams, is that you want to prove y1 minus y0 equals 7, n2. And so what you do instead is you say, okay, y1 minus y0 equals 7, n2. Okay, what's n2? It's negative n1. Okay, y1 minus y0 equals 7, negative n1. Okay, I'm going to negate both sides. Y0 minus y1 equals 7, n1. Great, this is true. This will cost you points. Do not do this. Do not do this on... Why is this wrong? The thing I wanted to show, the property I wanted to show, was that y1 minus y0 is equal to 7, n2. This is not a proof. A proof always starts from what you know and proceeds at the end to what you want to show. In this case, I started from what I wanted to show and ended up with something that I knew. Therefore, this here is not a proof. This is a backwards proof. And it will definitely cost you points on the exam. How would I write this correctly? It was to start from what I know, start here, and proceed to what I want to show. So one way to write this proof is actually to start from here and then step by step do this. Or a different way, which is also valid, is if you're proving that like something is equal to something else, would be to start from the left-hand side and just evaluate stuff until you can get to the right-hand side. Notice how at every step of this evaluation, I can justify this equal sign with a reason, either a standard algebraic manipulation or with something that I already knew. This here is a standard algebraic manipulation. This here I use something that I already knew. This is a standard algebraic manipulation. And this is using this fact. So this is like algebra. This is from here. This is something that I know. This is also algebra. And this is something that I know. Notice here I have completely justified this line with either standard algebraic techniques or references to previous statements in the proof. Notably, I said references to previous statements in the proof because previous statements in the proof are things that you already know. Subsequent statements in the proof are things that you are deducing. So it is invalid to write this statement by referencing things underneath in the proof, because those are things that you're going to deduce. All your equal signs should, in effect, even if you don't write them out, in your head, you should be able to justify every single equal sign by either a standard algebra thing or a statement that you already knew. Do not start with the thing that you already knew. No, do not start with the thing that you want to show and just manipulate it down to something that you already know. That is a good way to discover the proof. In effect, what you've done here is that you work backwards. But that is a good way to discover the proof. But at least if you're running out of time on a test and you know you did this, just read from here to here. Just like draw an arrow, be like read from here to here, so that we know to start from here and read up to here, to signal that you started from what you knew and ended up with what you wanted to show. All right, I'll keep this up. Erase this. I'm going to now do for you a proof for transitivity. Yeah.
Part that you know.
Yes.
You set M2 to negative M1.
Mm-hmm.
How did you come up with that? Like, what is the process of coming up with that? Is it like just experimenting?
Right. I think it's a little bit of an experimentation. Yeah, so I don't have I'm sorry, can't give you a clear, like I knew what I wanted was like the negation of something that I already knew. So that's why I just set it to the negative.
So if there are other options that we could like set M2 to and then still get it.
You could say like set M2 equals to something else, but chances are the proof is just not going to be able to go through.
But it only works if we set M2 to negative M1.
I can't think of something else that would work. Yeah. Yeah. Yeah.
But just wondering, there isn't like a technique to come up with that example to say, okay, maybe if I go this route, this example would have a higher probability of working, right?
The technique is so dependent on the definition of the relation that we are using that I hesitate to give you one, just because it would be so restricted to us. It would be restricted to such a restricted class of relations that it probably won't be useful in any general sense. Yeah.
It's kind of a small thing, but when you wrote the definition for this specific relation, I guess like writing the definition for any relation, it should be if and only if, right?
Yes. Yeah. All right. Let me also do the proof for transitive. Yeah. Oh yeah.
Are there any relations that are reflexive, symmetric, anti-symmetric, and transitive?
It's a good question. But maybe like we can think about it offline. Yeah. And okay. All right. Okay. So I want to also do the proof for transitive for you. Yeah. And I think this will also reference your question about how did I kind of come up with this? And really, I think the best answer I can give you is it is like a bit of an experimentation. There is some level of like say engineering in coming up with the right example. And I think it's maybe going to be a little clearer here for this transitive proof. How do I prove this? Again, what is the statement? Is a for all statement. So I take arbitrary x, y, z inside what's x? Well, x, remember, as we did, is n squared. What's the property that I want to show? X, move this up. Good, okay. what's the property that I want to show? XRY and YRZ implies XRZ. I'm just going to quickly breeze through the kind of various, like bookkeeping tactics that we've already covered. I'm going to rewrite X as equal to X0, Y0. Y is equal to X1, Y1. Z is equal to X2, Y2. This here is an implied statement. I'm going to assume XRY and YRZ. I'm going to prove XRZ. What does it mean to prove XRZ? It means there exists an I'm going to say M3 such that X2, XRZ means X0 minus X2 equals to 5M3. Similarly, there exists an N3 such that Y0 minus Y2 equals 7, N3. I hope you have been noticing that doing these two proofs, they're basically the same. So because this is an and statement, I have to prove this and this. I hope you've been realizing that these two proofs are almost basically the same. So I'm going to do one of them just to save time. And just know that you also have to do number 2, but I'm just going to omit it. 1 here. There exists M3 such that X0 minus X2 is 5M3. How do I prove there exists statement? Give an example, show that it works. Before I do that, I want to rewrite these in terms of their definition so that I have them. So I have this M1 where X0 minus X1 is equal to 5M1. And I have this, and what does it mean? And there's a similar one for the Y's here. So I'll say similar for Y's. And so this is XRY gives me this. For YRZ, there exists an N1 such that X1 minus X2 is equal to 5. No, not N1, M2, 5M2. And here I have a similar one for the Y's. Turns out I won't need those to do this first proof. And so I'm omitting them, but I hope it's clear that how to write an analogous statement for the Y's. Now to your question about how am I going to come up with this example M3? So here I'm going to show you, I'm going to do some scratch work to show you how am I going to come up with this M3? So I want X0 minus X2 is equal to 5M3. Okay, what do I know? I know this. I know X0 minus X1 is 5M1. I also know X1 minus X2 is 5M2. How am I going to get this? How am I going to this is stuff that I can work with. How am I going to get this thing? And so I'm thinking I really want an X0 minus X2. What I know, I don't have an X0 minus X2 here, but how can I combine the stuff that I know to get an X0 minus X2? Well, what I can do is I can add these two equations, and I can get an X0 minus X2, which is equal to 5M1 plus M2. And now I'm looking at this, I'm saying, this is really what I want. I get my X0 minus X2, and what's my M3? My M3 is just my M1 plus M2. Having done this scratch work, now I can do this part. What's my M3? Set M3 equals to M1 plus M2. Show that this works. X0 minus X2. What's X0 minus X2? Well, now I sort of use this kind of scratch work that I did. How did I get an X0 minus X2? Well, it was by adding this and this. X0 minus X1 plus X1 minus X2. Now, what's X0 minus X1? It's 5M1. What's X1 minus X2? It's 5M2. What's this? I can factor this. 5M1 plus M2. Oh, but M1 plus M2, it's M3. It's 5M3. Therefore, I've shown X0 minus X2. Therefore, I've shown that M3 satisfies this property because x0 minus x2 equals M3, 5M3. Recall, I can justify every single one of these equal signs with either an algebraic manipulation or something that I already know. The algebraic so here to here, this is an algebraic manipulation. This is something that I already know. This is an algebraic manipulation. This is something that I already know. And so that essentially gives you the proof for transitivity. I want to now give you an example for how to say, give a counterexample. If something is false, how do I give a counterexample? And so in this case, it's not anti-symmetric. So how do I give a counterexample for a for-all statement? To give a counterexample for a for-all statement, all you have to do is show that one thing, one xy. So this says every xy satisfies this property. To give a counterexample for a for-all statement, all I have to say is, if I can show you one xy where this doesn't work, then I know that this statement is false. Because this statement asserted that every xy satisfies this property. If I can show you one xy doesn't work, then this statement is false. That applies for all the other properties as well. Notice all these other properties involve for-all statements. So to negate them, to show that they are false, you just need to simply find one example where this property here is false. I'm going to notice the structure of these properties. They're all for-all statements, property. For all and property. So if I want to show that they are false, you give an example. To show that a for-all statement is false, you give an example, and you show that this property doesn't hold. So counterexample is always find an example of an x or xy or xyz and show that the property doesn't hold. I'm going to give so a counterexample is always, let's see if that's visible. A counterexample is always find something here where this doesn't hold. I'm going to do this for anti-symmetric. Anti-symmetric, I'm going to find an xy. So step one is finding that xy. What do I need? I need an xy inside x. Remember, what's x? Ordered pairs of naturals. And what about these ordered pairs of naturals? I need x r y and y r x to be true, but x not equal to y. So I need to find some xy inside here where x r y and y r x, but x is not equal to y. Remember, to negate an if statement, you need to find something where this is true, this is false. In this case, it's pretty easy. To show that x rx is not true, you need to find some x where this xx is not inside the relation. All these other if statements, how do you show an if statement is false? Find something where this is true, this is false. This is true, this is false. Or this is true, this is false. Anti-symmetry, I need something, this is true, this is false. So what's x, r, y? So remember x, y, what's x? Well, x is some kind of x0, y0. Y is some ordered pair x1, y1. What do I need? I need x0 and x1 to kind of differ by a multiple of 5. Y0 and y1 to differ by a multiple of 7. And I need the reverse to be true. And also x is not equal to y. I'm going to give this example here. Let's say x is 2, 3. Let's say y is 7, 10. Is x or y? So step one, you give the example. Step two is now that you show that the required conditions hold. Here, notice I've written down the required conditions in a way of saying, what does it mean for it not to be anti-symmetric? I need this and this true, this false. So the required conditions, this and this true, x equals y false. So step one in giving so when you give the counterexample, step one is provide the example. Step two is to show that your example satisfies those needed properties. So so the way of doing this probably most effectively is first writing down your required conditions, looking at your definitions and saying, what do I need about my example? What are the required conditions for my example? Use those things to try to come up with an example. And then say this example, and then explain why this example satisfies my required conditions. So do I have x, r, y? Well, I have x, r, y because say like 2 minus 7 equals 5 times -1. So this here, that's my M1. And also 3 minus 10 equals to 7 times -1. Here's my M2. So this is for x, r, y. Do I have y, r, x? Well, 7 minus 2, y, r, x, x1 minus x0. 7 minus 2 is 5 times 1. This would be my M1 for this case. 10 minus 3, that's 7 times 1. This would be my n, not M1, M2, M and n. So here, how do I know x, r, y? Well, 2 minus 7 is 5 -1. That's my m. 3 minus 10, that's 7 times -1. That's my n. Do I know y, r, x? 7 minus 2 equals 5 times 1. That would be my m here. 10 minus 3, that's 7. That would be my n here. So I know x, r, y, I have my m and n. Y, r, x, I have my m and n. Is x equal to y? Well, 2, 3 is clearly not equal to 7, 10. 2 is not equal to 7, 3 is not equal to 10. Therefore, I have satisfied all three of my required conditions. So I can number them. I can say this is condition A, this is condition B, condition C. And so this is condition A, condition B, condition C. And this here is a very short form explanation of why my example satisfies the needed conditions to give a counterexample for anti-symmetry. And before I conclude this section on relations, give you a little bit, before I conclude this section on relations, I want to give you one more example. I'm not going to do all the proofs just for the sake of time, but I just want to give you one more example of why I said, now I think I've erased it, why I said not to interpret things too literally about the less than or equals to and greater than or equals to. But even before that, I want to give a little bit more about, I want to talk a little bit more about this example. So I'm going to keep this example 1 up here, but I'm going to erase the proof for the reflexive. And I want to say that R here, this R, is an equivalence relation. How did I show that it was an equivalence relation? Was that I proved that R was reflexive, the proof formerly here, symmetric, transitive. R is an equivalence relation. I want to give you a few more definitions and use this example to show you very clearly like what these definitions mean. When you have an equivalence relation, you have equivalence classes. And what are equivalence classes? Equivalence classes are sets of elements which you know are all, quote unquote, related to each other. I use this word related now fairly freely in the sense that because an equivalence relation effectively encodes what it means to be equals. So what's an equivalence class? An equivalence class is the set of all elements which are, quote unquote, equal to each other. Now notice these are not like, notice I use the word equal in quotes because in this case we said that 2, 3 is related to 7, 10. And since R is an equivalence relation, I could say like 2, 3 is quote unquote equal to 7, 10. And what does it mean to be quote unquote equal? How do I define what quote unquote equals mean? Quote unquote equals is this relation R. And so so saying that R is an equivalence relation lets you say that R is a way of defining what it means to be equal. And so what's an equivalence class? An equivalence class is effectively the set of all elements which are quote unquote equal to each other. What's quote unquote equal? What do I mean by quote unquote equal? What I mean by quote unquote equal is defined by what R is. And so, for example, I'm not going to write down exactly what, I'm going to omit the formal definition, which is, I think, contained inside the PDF lecture notes on Canvas that Matt and Noah prepared. But I'm just going to give you an example. Is what's the equivalence class of 2, 3? What is this notation? This notation says the equivalence class of 2, 3, what is this? This is a set of what? Of all the elements, quote unquote equal to 2, 3. And I want to point out to you various components of this notation. This 2, 3 says the set is all elements quote unquote equal to 2, 3. So I write 2, 3 here to say, I want all the elements quote unquote equal to this. I write an R here to signify how am I defining quote unquote equal? I'm defining quote unquote equal via the equivalence relation R. Notice if R is not an equivalence relation, it is essentially meaningless to think about it as quote unquote equals. If R is not an equivalence relation, do not use the intuition quote unquote equals. It just like won't make sense. But if R is an equivalence relation, you can think about it as being quote unquote equals. What's the equivalence class? This says the equivalence class of 2, 3 is all the elements which are quote unquote equal to 2, 3. So what are the elements inside here? They're ordered pairs of natural numbers. So and why are they ordered pairs of natural numbers? I said all elements. What are the elements we are comparing? We are comparing ordered pairs of naturals. So each of these things is an element which is quote unquote equals to 2, 3. What are the elements we are comparing? Ordered pairs of naturals. And so what is this set? This set is a subset of n squared. I want to also give a second definition when you have an equivalence relation. The second definition is that of a quotient. And the way I write this quotient is I write first the set of elements that I'm comparing. I write quotient R. So here, this is what are the elements I'm comparing. Here, this is what is my relation. The words equivalence class and quotient really only apply whenever you have an equivalence relation. Don't do this if R is not an equivalence relation. What is this? This is the set of all equivalence classes of R. So what would the quotient here look like? I can't really write it out, but here, so what is it? It's a set. It's a set. The individual elements here, each of these are equivalence classes of R. So each of these things here are subsets of the natural numbers. So can I say that this is this true? This is not true, because this set is not a subset of n squared. Each of these individual elements are equivalence classes. And equivalence classes are subsets of n squared. Equivalence classes are a subset of the set of all things that I'm comparing. These here, each of these individual ones are subsets of n squared. But is this a subset of n squared? Well, how do I test if something is a subset? Well, I go through each of these elements here, and I say, is this inside n squared? Is this inside n squared? Is this inside n squared? Is this thing inside n squared? It's not, because what's here? This is a whole set of a bunch of ordered pairs here. This is another set of a bunch of ordered pairs here. This is another set of a bunch of ordered pairs here. Remember, these are what the equivalence classes look like. Is this thing inside n squared? No, because this is a set. N squared contains elements which are ordered pairs. These two, like this, these elements look like this. These elements look like this. This is not inside here. And so I think just to repeat what a quotient is, the quotient is a set. Each element is an equivalence class of R. I want to give one last thing, which requires a different example. I'm going to now do a second example of a relation S, also on n squared. And I'm going to say x0, y0, S, x1, y1, if, say, x0 is less than or equal to x1, y0 is less than or equal to y1. And here, I'm not going to prove it here, but this here is a partial order. And so a lot of times when you have a partial order, remember a partial order intuitively, you could say it's effectively like less than or equals to. So that's why I'm going to say like S. And so a lot of times the notation here, we're not going to do something like this. We might say a relation curly less than or equals to. This is straight less than or equal to, this is curly less than or equal to. What I want you to take away from this example here, you can prove this as a partial order. I'm omitting the proof just for the sake of time. What I want you to take away from this example, so when you have a partial order, curly less than or equals to, a lot of times it's helpful to try to use your intuition to think about curly less than or equals to as actual less than or equals to. But it's important that when you really test whether something is a partial order, you go back really to testing each of those individual properties that you need for a partial order, namely reflexive, anti-symmetric, transitive. You really want to really rigorously test whether you're a partial order. You have to really go back to these properties. Intuitively, you can kind of, if you want to come up with a counterexample or you want to see if it's false or something, intuitively it helps to think about this as sort of like a less than or equal to. But to justify whether your intuition is correct, you have to go back to these properties. And I want to show you one reason why it's really important to go back to these properties. Normal less than or equals to, you either have A less than or equal to B or B less than or equal to A. This is true for normal less than, this is true for the normal less than or equal to straight. But for a partial order, something like this is not necessarily true. Not necessarily true. For curly less than or equals to. And I want to show you why. I know that, say here, 2, 3. Let me do this one. 2, 5. And 4, 1. Is 2, 5 curly less than or equals to 4, 1? Well, no, because 5 is not less than 1. Is 4, 1 curly less than or equals to 2, 5? Also no, because 4 is not less than or equal to 2. And so in a partial order, it is possible to have, in a partial order, it is possible to have x not curly less than or equal to y and y not curly less than or equal to x. But in the normal less than or equals to, it's not possible. You can't have x, you can't have a less than or equal to b. Well, in normal less than or equal to, this is never possible. You can't have x not less than or equal to y and y not less than or equal to x. You either have x less than or equal to y, or you have y less than or equal to x. But in a partial order, so regular less than or equals to, this is not possible. In a partial order, it's possible to have this fairly unintuitive thing where you have x not curly less than or equal to y, and y not curly less than or equal to x. Okay, I want to take a few minutes, like 3 minutes break here as we conclude this section. I know I said I would end at 8:30, but I know I started a little late. So in order to cover everything, I'm still going to, so Matt originally posted that we would have this room until 9. And so I'll go up to 9 if I need to. But everything is recorded. So if you ever have to leave or anything like that, the recording should be also available. So I'm going to resume at around like 7:50 or so. Just give me a second. I want to just erase the board. Oh, Ethan, is it possible if I try to answer your question at the end?
So I was wondering if we're gonna do combo now.
Huh?
We spent a lot of time on relations.
Yeah,
I
I
tried
tried
a lot
to.
of class already. A lot of us already like done a lot of relation stuff.
Okay, yeah.
And we haven't even very little combo stuff.
Yeah. So I mean, I plan to cover. Yeah, the automata part, I'm not going to spend.
Yeah, I think we spent a lot of time on account of my relation. We spent a lot of time.
Yeah. So I'll make sure to.
So yeah.
Huh?
Do you see what I texted?
No, I haven't. Okay. Yeah. Just let me. I just want to clear up the board. I'm going to start pretty soon. Yeah.
Is NT relation
No, unless you have an intersect.
so if the initial set is
Yeah.
that any relation not or that's not really.
It's such a weird edge case. But like, as long as the set that of elements that you're comparing is non-empty, the empty relation is not reflexive.
The empty relation is not.
Right, because even if you have one element, say like one, then you need like the element like 1R1. Like,
Oh, I see.
All right. I want to go ahead and get started. So I want to go ahead and get started with the automata section. And I'm going to primarily focus on two techniques inside the automata section. And those two techniques are, the first is to convert an NFA into a DFA. The second thing is to convert an NFA into a regular expression. And so I'm going to try to focus on, and so those are basically the two main things that I want to cover in terms of review. I might touch on a few other topics, but those are really just the main things that I'm going to focus on. I'm going to skip the like for relations. I think because we were doing very formal proofs with relations, it was important that we started with the very foundational, basic kind of formal level of what a relation is. But since here in this automata section, because the two procedures that I want to present involve, this kind of not so much proving things about automata, but manipulating automata, I'm going to skip the section on formalism, because the formalism for a finite automata is pretty like messy. You have like a 5-tuple of like alphabet, start state, and all of that. I'm going to skip that, and I'm going to go straight into just explaining the various procedures. I want to first just mention, so in this section on automata, in most of the examples that I'm going to give, the alphabet is going to be 0, 1. In other words, the only characters that we can read are going to be 0 and 1. A DFA, I'm just going to draw an example here for a DFA of our start state. Say we do something like this. 0, S1, S2, 0, 1, 1, 0, 1, 0. Let's see, this is my final state. I'm going to draw an example of an NFA. Zero, 1. I'm going to just point out a few differences between a DFA and an NFA. In a DFA, every state, so for a DFA, every state has to have a transition for every character in your alphabet. Every state has a transition for every character in my alphabet. Whereas in the NFA, this is not necessarily true. Notice here, every state contains a transition for 0 and 1, 0 and 1, 0 and 1. So a very good thing to check when you are like making a DFA is to verify that every state has a transition for every character in your alphabet. In this case, notice that I checked whether there was 0, 1 transition for this, a 0 transition, 1 transition for this, a 0 transition, 1 transition for this. In NFA, that is not required. In a DFA, you accept when your string ends you up in a final state. In an NFA, you accept when there is some path to a final state. In a DFA, everything is deterministic. So if you were given a string, because I want to say not only does every state have a transition, every state has a unique transition. In other words, you can't have two zeros. Like you can't have two zero transitions. You can't have like two one, like every state has 1 0 transition, 1 1 transition. If my alphabet says 0 1 2, I would need 1 0 transition, 1 1 transition, 1 2 transition. And so because a DFA is, for lack of a better term, really just deterministic, if I were to read you a string and you were to travel along the DFA, you accept when your string, when I conclude my string, as I read to you the string, you start your start state and you hop around along these states. When I conclude that string, you accept that string if you stop inside a final state. In an NFA, because I can have, let me just draw this here just for clarity. So here I can have two zero transitions and no one transition. Here I have a zero transition and a one transition. Here I have no transitions at all, actually. And in an NFA, you accept the string if there exists some path for that string to end up in a final state. So for here, I'd say the string 0 0 is accepted. And what is the path for 0 0 is to go 0 0. It doesn't matter that there's another path that goes 0 0 and ends up into a non-accepted state. As long as there's one path for that string to go into an accepting state, that string is accepted. The second thing is that in an NFA, if I were to read you a character for which there was no such transition, it is an automatic reject. So you auto reject if you read a character for which there is no transition. Now, one clarifying thing is that this rule takes precedence over this rule. Namely that if you have a path for that string to end you up in a final state, it doesn't matter if the other paths happen to have this. This is not an auto reject. If you have that, once you have that path, it is an auto accept. If you have like another path which causes an auto reject, if you have, say, two paths for your string, one of them causes an auto reject, one causes an auto accept, it's still an auto accept. So this auto accept rule takes precedence over my auto reject rule. I want to give you an example. Let's say we do 0 1 0. 0 1 0 is accepted. The path is 0 1 0. There are alternate paths. There are alternate things that could happen. What if I did 0 and I don't have a 1? Does that mean 0 1 0 is rejected? No, because my auto accept rule takes precedence over my auto reject rule. I know my path for 0 1 0, 0 1 0. Therefore, I auto accept. It takes precedence over any other possible path which could encounter an auto reject. So this is accepted. An example of a string which is rejected is 1. 1 is rejected because I start my start state and I read a 1, but there's no transition for 1. This is an auto reject. And there is no valid path to an accepting state for 1, for the string 1.
0 0.
All right, I'm going to now explain the two procedures. Yeah. Mm-hmm.
So S, let's say 0 0 1 rejected.
0 0 1. Yes, I believe so.
Well, is that but 0 0 takes us to a final state, and if we are in a final state, but we still have characters left, then we are auto rejected.
Ah, that's a good question. So 0 0 1 is So maybe I have to switch the boards. 0, 0, 1 is rejected because even though I can do a 0, 0 here, when I read the 1, is there a transition for a 1 here? There's not. And so it falls into my auto reject category. Any other questions about, yeah?
So it seems like also apply to the DFA. It seems like there's no
in the DFA, the rule is not so complicated because once you have your string, you get a unique path that's determined for your DFA because every transition is exactly, yeah. Sure, yeah. Oh, and of course, in my NFA, if there's no path to the accepting state and all your paths end up, even if you had transitions everywhere, but like all your paths ended up to a non-accepting state is also a reject. So that characteristic still carries over from a DFA. All right, I'm going to present now the two procedures that I think are important for the exam. One is an NFA to DFA conversion. And for this, I'm going to use similarly the examples inside the lecture notes. And that way you can complement, my explanation with the explanations inside the lecture notes. And also, since I've recorded this, if there's any confusion, that way you can try to match up these things. Both the video and also the explanations inside the typeset lecture notes that Matt and Noah prepare. So for this, I'm going to use this NFA. And they use a different alphabet A and B. So I'm just going to convert it to still use 0 and 1. 0, 1 is S0, S1, S2, okay, so I have a 1. All right. So in my DFA, I have here the names of my states, S0, S1, S2. In my DFA, what are the names of my states? The names of my states are going to be subsets of the set S0, S1, S2. So this is my set of states. What are my states going to be named? The names of my states inside my DFA, the states are going to be named with subsets of S. Notice here, my states are named with elements of S. In my DFA, my states will be named with subsets of S. We start. So I'm just going to list out here a bunch of points. You're going to start at your state. The set containing S0, the set containing my start state. And so there are different ways of doing this, but the recommended way, in order not to even for a 3-state NFA, if I were to write out all possible states inside my DFA, let me make these. If I were to write out all possible states, not even all possible, all potential states I might have to use for my DFA, I'd already have to write 2 to 3 states. Quickly, if I had 4 states in my NFA, you had 16 states, and 5 states in my NFA, 32, states that you start drawing inside your DFA. And so the recommended way of doing this is not to first say, oh, my states need to be subsets of S, and then write out 8 different states of all the subsets of S. Instead, what we're going to do is we're going to do this lazy evaluation method, which is to add states as necessary. So that's why the second thing was to start at state set containing S0. And remember, a DFA, I need exactly one transition for a 0, and exactly one transition for a 1. So every state that comes up here needs exactly one transition for a 0, needs exactly one transition for a 1. This state here, so how am I going to do this lazy evaluation? I'm going to start with my state set containing S0, and I'm going to say I need a state, I need a transition with a 0, I need a transition with a 1. That may induce the inclusion of more states. Then those additional states need a transition with a 0, need a transition with a 1, and basically you keep doing this until you don't need to add any more states. So how am I going to add in, rather than write it out, I'm going to add in my 0, 1, or all necessary, add in all necessary transitions. And instead of writing out the procedure, I'm going to just verbalize it here. What's my transition 0? My transition 0 is going to go to a state. If I think about this state's name as S0, I'm saying, if I were in one of these states and I read a 0, what are all possible states which I could end up in? In here, there's only one element. There's only S0. What are all possible states I could end up in if I read a 0? Oh, I forgot a self loop here. If I read a 0, all possible states I can end up in is just S0. So I'm going to come back here. How about 1? If I were inside S0, all possible states I could end up in if I read a 1 is S0 or S1. So that means that I need to draw another state, S0, S1, to say, when I read a 1 and I'm sitting inside S0, these states that I could end up in are S0 and S1. All possible states, when I start in S0 and read a 1, all possible states I could end up in are S0, S1. Notice here, my first state here has a 0 and a 1 transition, but now I added another state. This state now needs a 0 transition, a 1 transition. How do I figure that out? What's the 0 transition here? It's saying, if I'm inside S0 or S1, I could be in S0 or S1. What are all possible options for states I could be in after I read a 0? If I were inside S0, so where is this going to go? So if I were inside S0 and I read a 0, I would be back inside S0. If I were in S1 and I read a 0, I would be in S2. So what are all possible states of, all possible states of S0 going to, all possible states of being in S0, reading a 0 is S0. All possible states of S1, reading a 0 is S2. So this transitions to S0, S2. Now I still need a 1 transition here. All possible states for S0, reading a 1 transition. All possible states for S0 reading a 1 transition is S0, S1. All possible states reading 1 transition for S1 is S2. So a 1 transition here is going to get me to a state S0, S1, S2. Intuitively, how I make these transitions is I say, if I were in any of these states and I read a 0, what are all possible states I could end up in? All possible states I can end up in reading a 0 for S0. Union, all possible states I could end up in reading a 0 if I were in S1. And that would be the new set. That would be the new state I end up in. Now I've induced 2 additional states. And so I need to fill in the 0 and 1 transitions for this. S0, S1, S2. If I were to read a 0, what are all possible states I could end up in? Well, S0, I would end up in S0. S1, I would end up in S2. S2, nothing. So it's S0 or S2. How about 1? Or here, I can end up in S0, S1. This I can end up in S2. This, nothing. So S0, S1, S0, S1, S2, nothing. How about for the S0, S2 state? S0, S2 state. If I read a 0, I can end up in S0, nothing. So I go back to my S0 state. If I read a 1, I can end up in my for this one, I can be S0 or S1, so nothing. So my total is S0, S1. Great. Are there any more transitions I need to add in? There are no more transitions here. And so this almost completes my DFA. The last thing I have to add in is assign final states. What counts as a final state? I look at the states which are contained inside each one. If a state contains an original final state, you mark it as final. So here, the only final state is S2. So I simply look inside each one and say, which one contains an S2? This one contains an S2. It's final. This one contains an S2. It's final. If you had more than one final state in your DFA, S1, S2, you simply look for any state here. If you had S1 as a final state, S2 as a final state, then all you have to do is just look inside here and say, which state has an S1 or which one has an S2. As long as it contains one of them, you circle it. It's a final state. So assign final states. Any state in your NFA containing a final state of DFA. Doesn't have to be all your final states, just containing one final state of your DFA is marked final. Okay, I'm going to move this board up, and I'm going to present also the second procedure, which is converting NFA to regular expression. Yes.
Can you repeat what happens if, let's say, on that NFA,
yeah,
we didn't have any arrow for 1. It was just 0.
Good point. So like, if I have the issue of let's say you're in a state and it's like, where can you go with for 1 and nothing? There's just nowhere to go. Then remember, we have to mark these states with subsets. One such state is the empty set. So you could end up nowhere. If you look, say if you had a hypothetical example where S0 and S2, when you rid of 1, there's just no transitions. You just couldn't end up anywhere. Then you would end up in a set. Then you would end up in a state, empty set. The empty set, notably, is never a final state because the empty set doesn't contain any states at all.
And,
yeah.
Also, let's say if in the exam they want to trick us in some way, and they give us an NFA that is almost like a DFA, perfect, that has all the arrows, and they want to convert it to an NFA, we still have to put every state into subsets.
I would very strongly just use this method. This method is pretty good on against tricking you, sort of thing. Right there, this method, if you follow this method correctly, it will always work. Yeah. I want to now present the procedure for converting an NFA into a regular expression. This is NFA to regx. The example I'm going to use All right, this is the example I want to use for this. To convert an NFA, so this should be almost basically exactly the same as in the lecture notes. But so NFA to regular expression. Step 1, you want to make your final state. And so recall what we're doing is we're progressively constructing this kind of quote unquote generalized NFA where the transitions can contain regular expressions. Step one is to make a unique final state. So here, I'm going to redraw this. So my step one is make all the original final states. So if there's no unique final state, I can write a little more. So if final state is not unique, so if the final state is already unique, I don't think you have to do anything. But if the final state is not unique, you make everything non-final. And then add a final state. So here, I'm going to make everything non-final. I'm going to add a final state. I'm going to call this S3. And how do you make your transitions? So I'm just going to say like add the transitions. And how do you make your transitions is I'm going to look at each final state here. And I'm going to look at what state, like I'm going to look at every transition entering this final state. Every entering transition. So every entering transition to a final state. Take into account where it's from, like what character is on the transition. My S1 here. I'm going to think about every entering transition into this final state. One is, and I'm going to keep track of two pieces of data: where it's from, what character is on the transition. And an entering transition here is this one. It's from S0 and it's transition 0. I'm going to take that information and I'm going to put it here into my new final state. From S0, transition 0. I have another one here, from S1, transition 1. No more here. Let's do this one. Did I draw this right? Okay. Yeah. Here, from S0, transition 0. Oh, we already drew this one in. From S1, transition 0. So we need to add in another one here. I'm just going to do this. After I've done this, step 2, we want to delete. We want to delete the nodes. We want to delete states. And these states are the non-start, non-final. I'm going to delete these states one at a time. So what are the states that I have to delete here? I have to delete S1. I have to delete S2. So let's delete S1. How am I going to delete S1? I'm now going to construct a table. And I want to look at every combination of in arrow and out arrow, excluding self loops. So excluding self loops, I'm going to make a table of every combination of how to come in, how to leave. Because we have to come in and we have to leave, we're going to exclude all the self loops. I'm going to make a table here. So I'm going to say in and out. So I can come in from S0, transition on 0. I can leave. So this is actually two different transitions. I can leave going to S2, transitioning on 0. So the only in arrows are coming from S0 transitioning on 0. Remember, I'm excluding self loops. So, and my out arrows, how many out arrows do I have? I have 3 different out arrows, 1, 2, and 3. So there are two things here. So every combination, S0, 0, S3, 0, and S0, 0, S3, 1. Every combination of in arrow and out arrow, I make a row in my table. Here I have 1 in arrow, 3 out arrows, multiplication rule, 3 entries in the table. Now what I do is I draw this NFA, and I delete everything involving S1. S0, S3, S2. So I have a transition here, 0. I have a transition here, 0, 1. Everything else gone. I don't think this is very clear. So I'll put that. And then what I'm going to do is I'm going to add in arrows for each of these things. Now, how do I add in? So I'm going to, so what's my corresponding regex for each of these arrows? My corresponding regex, this is in here, out here. So this would be 0, 1 star, 0. This one is here to here, 0, 1 star, 0. And similarly here, it should be 0, 1 star, 1. How do I add them into this NFA? Start from S0, go to S2, put this regex on top. Start from S0, go to S2, and add this regex. Because I already have a 0, I can now do 0 or 0, 1 star, 0. Same thing here, S0, S3, I can do 0, I can do 0, 1 star, 0. Same here, S0, S3, 0, 1 star, 1. 0, 1 star, 1. Repeat this again for deleting S2. I'm going to consider every combination of in arrow, out arrow. There's only 1 in arrow and 1 out arrow. My in arrow comes from S0 and transitions on 0 plus 0, 1 star, 0. It leaves to S0 on 1. What's my corresponding regex? Well, there's no self loop here. So I start from S0, I go back to S0, and I do 0 plus 0, 1 star, 0. Follow no self loop, followed by a 1. So now what I do, I draw everything except for my S2. I draw everything except for S2 because I'm deleting S2. Here, 0 plus 0, 1 star, 0 plus 0, 1 star, 1. And here it's 0 plus 0, 1 star, 0, followed by a 1. Once I end up here, where there's only a start state and a final state, I can simply read off the regular expression. What's the regular expression here? Well, I can loop this, 0 plus 0, 1 star, 0, 1. I can loop this as many times as I want, and then come here. 0 plus 0, 1 star, 0, plus 0, 1 star, 1. There are a few different cases for what you can end up with, but I think that once you end up with just a start state and a final state, it should be pretty clear what the regular expression is. But the cases are enumerated inside the lecture notes, and so I don't think I will go over all 4 of the cases. Yeah. Mm-hmm.
Yeah, I have a question. What if the start state itself is a final state?
Okay. If the start state itself is a final state, I guess since you asked if I had something like this,
yeah,
and let's say I had a regular expression R1 here, this would correspond to the regular expression R1 star. It's like a loop around R1.
Like, so we still need to combine the final stage at the start stage and another stage of the final stage.
Sorry?
Like, for example, the start state is the final stage, but it's not the only final stage. Do we still need to combine the final stage?
By the time you reach here, so by the time that you reach here, you only have one final state. Other than, by the time I'm blanking on an example in which you could end up with. So the lecturers mentioned that it's possible to end up with a DFA that, with an NFA at the end that has, I believe, 2 final states. I'm blanking on an example of how this could occur, but I imagine it can. And rather than try to come up with it right now, if we could talk about it after if we want to. Sure. Yeah. Okay, sure. Yeah. Yeah. All right. Any other questions about this? Or, yeah. Oh, yeah. Because here I'm looking at what are my in arrows? What are my out arrows? And I need every combination of pair of in arrow and out arrow. So if I have 1 in arrow and 3 out arrows, I need 3 rows in my table because I need every possible pair of in arrow, out arrow. So then like I need this one and this one, this one and this one, this one and this one kind of thing. If I had 2 in arrows and 3 out arrows, I would need 6 entries in the table because I need 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3. Oh, yeah. Yeah.
Final state is not unique. We introduce another state, make it final. If it's unique, then we just use that as the final state.
I think if it's unique, you can still do this. So I maybe I don't need to say that if the final state is not unique, but I imagine unless there's some borderline edge cases which I'm not thinking about, you can go straight to the deletion. But I think if I want to be safe, I can probably just omit this. Yeah. I'm sorry, I'm maybe blanking on a little bit of these edge cases. So we really want like a definitive version as to like some of these like, borderline edge cases. I think it would be good also to look at the PDF lecture notes. Okay, so this concludes basically the stuff that I want to talk about for automata. There's one other very, very like ancillary topic. I'm just going to mention it very briefly. Like I'm going to spend like a minute or two mentioning it very briefly. And after that, we'll move on to talking about combinatorics. Maybe I shouldn't have said it was ancillary, but I think it's a fairly small kind of topic, which is to talk about, just determining if you were to look at a language, whether or not it's regular or not. And I'm sure you're quite familiar with something like this, that you know that this language is not regular. And how do you know it's not regular? Is because DFAs can't count. DFAs can't count, but I hope that you can for this exam because counting is on it. The DFAs can't count because the sort of idea of the intuition, and so be careful because this is intuition, that I think this thing is not right, that I feel like this one is not regular, is because as I'm reading the string, what does my DFA need to do? My DFA needs to first essentially count how many zeros there are before I can, verify whether they're the right number of ones. Now, DFAs can count up to finite values. Like if you want to check if there are 5 zeros, you can count up to 5. But they cannot count infinitely because the DFA cannot count to an infinite number of states. Notice in this language here, I need to count up how many zeros there are, but I don't know how, this number of zeros is not bounded. So that means my DFA better be able to count to any number as big as possible. DFAs cannot do that. DFAs can count up to finite numbers. So if you set a bound and you say that, okay, only up to say like 5, then DFAs can count that. But if your DFAs need to be able to count to an unbounded number of zeros, your DFAs are unable to do that. In this language, your DFAs need to count an unbounded number of zeros because it needs to count the zeros, up to like 1 or 2, or like your n squared can get as big as you want. And what if your n squared is like 1 billion? Then your DFA better be able to count up to 1 billion or 1 trillion, and then figure out how many ones have to follow. Because here, the number of zeros that my DFA has to count is unbounded. Like, I can't just say my DFA only has to count to 1 billion. Because what if I come in with a trillion zeros and 1 million ones? My DFA still has to be able to count those trillion zeros. Even if it could, how about 10 to the 16th zero, 10 to the 18th, right? So because here the number of zeros that I have to count is unbounded, my DFA cannot count in an unbounded fashion. And that's sort of an intuitive way of figuring out whether your DFA can actually, whether or not this is a regular language. The alternative is to think about the pumping lemma, but I think for a true-false question, it's probably a lot more work than you want to do to go through the whole pumping lemma business. I'm not going to dwell on this too deeply because I think for the most part, if you look at something that looks like this, like 0, 1, 1 to the like n cubed plus n squared, I'm pretty sure you almost sort of like intuitively feel that this is not regular because I have to count up the number of zeros before I can determine how many ones there are. And that counting, this is an important point, is that the counting is unbounded. I have to be able to count to, no matter how many zeros I come in here, I have to be able to count all the way up to 0. DFAs can count up to finite values, but cannot count in an unbounded fashion. If you want more of these borderline cautionary examples for things like that, I think one of the practice questions that I prepared, has these kind of 0 to the n, 1 to a function of n kind of thing, and has you mess around with which ones are regular and which ones are not. Okay, so for the sake of time, I want to go immediately into talking about combinatorics, and then I'll try to answer as many questions as possible after. Oh, I have one question for you. Do you know if Stirling numbers are covered on the exam? Yes. Okay. I want to call your attention to a chart which is inside the lecture notes. And I'm going to draw this chart here. And this chart contains, this is a very useful chart, I think. Also, n balls, m bins, and the number of arrangements, injective, and surjective arrangements. So what lies here is the formula for the number of possibilities. And here is 3 of the combinations. So distinguishable, indistinguishable, distinguishable, and I believe distinguishable, indistinguishable. What I'm going to do right now is, rather than talk about multiplication rule, addition rule, and things like that, warn you that in combinatorics, it's very easy to trick people on combinatorics. And so I warn you that the way I recommend getting good at combinatorics is to just do a very, very large number of problems. They don't even have to be very hard. But you just have to see these things over and over and over again so that you're able to get the intuition and to feel about how to count these things. What I'm going to do here right now is I'm going to essentially kind of derive for you the formulas on this chart. And in doing so, demonstrate the various counting principles of, the various counting principles, multiplication rule, addition rule, and things like that. I'm going to derive for you to put you into the mindset of how to like, think about these counting problems, how to reason about them semi-intuitively. Part of it is really you have to like kind of feel that like, okay, this situation works with this situation works with this. If you just try to memorize this chart, it's very easy to trick you, because then suddenly if you can't figure out like whether like what are the balls, what are the bins, like, are they indistinguishable, are they distinguishable? Once you can't figure that out, you are like there's a very high chance you're going to get it wrong, because which formula are you going to use? Like if you're sitting here being like, okay, is it injective, surjective arrangement? Like if you're like sitting there and trying to reason about all these things, there's a good chance that you can get tricked, and there's a good chance that you might get it wrong. But if you are able to at least have some level of intuition as to like how these formulas come about, how do I work with them? Or like, then like you can still have this chart in your head, but to check whether this chart actually, like whether your answer makes sense, you can sort of fall back on this combinatorial intuition and see like, does this kind of setup make sense? And this intuition is only really developed, I feel like, through a lot of practice. And so here I'm going to derive for you the various formulas on this chart in order to show you sort of what is the intuition, the combinatorial intuition behind it. I want to start with n balls, n distinguishable balls, and m distinguishable bins. And I'm going to use a running example, which is, let's say you're in a school. I don't know if I have to say that. I mean, we're all in school. But let's say you're in a school. This is a very unfair school. And we are going to hand out candies to kindergartners. Now, these candies, they can be all the same, or they can be different. Also, two different people responsible for handing out these candies. One is the kindergarten teacher. One is the person who's working in the cafeteria. The person who's working in the cafeteria simply has a bunch of bins by which they need to put the candies inside. But the person in the cafeteria doesn't know, like the person in the cafeteria doesn't say like recognize the like students in the class. And so to the person in the cafeteria, all the individual bins for the students are indistinguishable. However, for the teacher, the bins are distinguishable because the teacher knows the students in the class. So we're going to use this as a running example, and we're going to talk about how many ways there are for each of these people to distribute the candies to the kindergartners. And in the cases of whether the candies are distinguishable or the candies are indistinguishable. Let's say that you're the kindergarten teacher and the candies are different. You have a total of n candies. You have m bins. Oh, and one more thing. Arrangement says total number of ways to put them in the bins. So some kindergartners can be sad and not get any candies. Injective means that nobody gets two. Everybody gets at most one candy, but some are sad because they don't have any. Surjective. Everybody gets at least one. Everyone's kind of happy, but some can get more than one. Life's unfair. So like, I don't know, like nobody's happy here. But anyway, so arrangements is total, no restrictions. Injective, everyone gets at most one. Surjective, everyone gets at least one. Okay. So first case, say you're the kindergarten teacher. You can tell the difference. You can tell the various students from each other, and you have n candies, m bins. So you can imagine this as like each student kind of has their own little like cubby kind of thing, like little like lunch bin kind of thing. You can tell the difference. All the bins are distinguishable, n different candies, and different candies. So the number of arrangements. How many ways are there to arrange this? Okay, so I have my various bins. Okay, bin A, bin B, bin C. So I have my various candies, etc. Each of these. Let me make sure I'm not switching this up. The number of each candy, I have m possibilities for where to put it. M possibilities for this. once I place this, for each placement of this, let's say I put this one here. For each placement of this candy, I have another m possibilities for here. For each placement of these two, I have another m possibilities for the third one. Another m possibilities. So that means it's m possibilities for this one, times m possibilities for this one, times m possibilities for this one. The number of arrangements, m raised to the power n. M possibilities for this candy, m possibilities for this one, m possibilities for this one. And for each choice that I can make here, if I were to fix this one in A, there would still be m for here. If I fix this one in B, there would again be n for here. Again, m for there. So, 1m, 2m, 3m, 4m, how many total m's? Well, m times m. So even by placing the two candies, I get m squared. Similarly, m cubed, m to the fourth, m to the n. Yeah.
Does that mean that for distinguishable candies and distinguishable bins, you can put all of them in one bin or distribute them among them?
Yeah. Anything so. Yeah. Notice here, it's very hard to remember this formula, m to the n. I mean, like, which is on top, which is on the bottom? Like, is m on top, n on the bottom? Like, during the test, it can be very hard for you to remember which one it is. But notice, if you are able to get this intuition behind it, then you know whether it's m to the n or n to the m. Each candy has m different choices for the boxes. And so once I fix the choice for this candy, I have m more options for this one. If I were to fix this in a different one, this would be another m options. If I first fix it in this one, then another m options. Well, how many times can how many different ways can I fix this one? Well, there are m different possible bins I can fix the first one. And for each one, I have m possibilities for the second one. Therefore, it's m times m, but generalize that all the way down, m to the n. How about injective arrangements? Everyone can get at most one candy. So if n candies, m bins, both are still distinguishable. Let's think about how to count this. There's m choose n ways to pick the people who get candy. M choose n ways to pick the people who get candy. So let's say I say this person gets candy, this person gets candy. Now everyone can get at most one. So let's say I have two. So there's m choose n ways to pick who gets candy. And then if I pick, say I have two candies here, how many ways are there to then distribute the n candies to the n people who get candies? There are n factorial ways to arrange this times n factorial. M choose n ways to pick who gets candy. And then once I have my n candies and my n people, how many ways are there to permute my n candies among this n people that get candies? N factorial. So this is pick who gets candy, who gets which candy. All right, I'm going to skip the surjective one for a moment in order to avoid using Stirling numbers as much as possible. I also want to fill in a fairly simple one down here. So this case here is distinguishable balls, indistinguishable bins. So now you're the cafeteria worker. You can't tell the difference between bins, but you still can tell the difference between the candies. So you can't tell the difference between the bins. And this is injective arrangements, which means you're saying at most, so nobody can get two candies. So you have all these candies, but you can't tell the difference between the bins. So in this case, this is probably maybe a little bit of a startling case. To you, because you can't tell the difference between the bins, this is exactly the same as this. Bins are indistinguishable. I've drawn them here so that they kind of seem distinguishable because they're sitting in some order. But really, the bins are indistinguishable. This is the same as this. It's the same as this. These are all the same. And you're going to put one candy into each one. You can't put more than one candy into a bin. So you're just going to put one candy into the bins until you run out. And that's the only way you can do it, because the bins are indistinguishable. It doesn't matter if I put like, if I had 5 bins and 3 candies, I could put my, candy 1, 2, 3, or, 1, 2, 3, or, like 1, 2, 3. Like it doesn't matter. I just put the 1 candy in each bin. That's the only way to do it, because the bins are indistinguishable. It doesn't matter if I do first 3, last 3. The bins are, you can't tell the difference between the bins. So there's one way if the number of candies is less than or equal to the number of bins. And you have more candies than bins, then you can't get an injective arrangement. So then n greater than. If you have more candies than bins, you wouldn't be able to get exactly one candy. You wouldn't be able to do this unless you had 2 candies in 1 bin. That is by the pigeonhole principle. And so therefore there are 0 ways for if you have more candies than bins. Now I want to present to you, I want to now cover essentially these 3 things. And these are all the balls and bins. These are all those like stars and stripes kind of formulas. I've encountered so many different terms for this same counting technique. Stars and bars, balls and urns, stars and stripes. I mean, but like, it seems like, the thing this year is stars and stripes. Let me start with this case. Indistinguishable, the stars and stripes technique really comes in when you're talking about indistinguishable balls, distinguishable bins. Let's say I'm going to demonstrate to you this formula. I'm going to use some physical numbers here so that makes things just a little easier. Let's say we have 10 balls and 4 bins. 10 stars. So before I convert this to stars and stripes, so there's 10 balls, 4 bins. Your bins are distinguishable, balls are indistinguishable. So I'm going to draw them as so. 6, 7, 8, 9, 10, all look the same. My bins, how many ways are there to put 10 balls into 4 bins where the balls are indistinguishable, but the bins are distinguishable? Since the balls are indistinguishable, all you are worried about is how many balls are inside a specific bin. All you are worried about here is how many balls are inside bin 1, how many balls are inside bin 2, how many balls are inside bin 3, how many balls are inside bin 4. It doesn't matter whether, if you have 4 balls inside bin 1, it doesn't matter whether it's these 4 or these 4 or these 4, because the balls are indistinguishable. So since the balls are indistinguishable, all you care about is how many balls in each bin. Now the bins are distinguishable. So if you have 4 balls inside bin 1, that is different from having 4 balls inside bin 3. But which of the 4 balls are inside bin 1 is irrelevant here. All we are concerned are the quantity of balls inside a bin. We are concerned with the quantity of which bin it is, but we're only concerned with the amount of balls inside each of the bins. We're not concerned about which balls are inside which bin. The way to think about this is to think about, if I have 4 bins, I'm going to draw 3 dividers to separate this row into 4 regions. Notice when I draw 3 dividers, I have 4 regions, region 1, 2, 3, 4. These 4 regions are distinguishable. They're distinguishable by their placement in the line. The balls are not distinguishable. So the balls here are not distinguishable. So how I can encode an option here is I can say, something like this. This is 2 inside the first one, 3 inside the second one, 2 inside the third one, 3 inside the fourth one. Notice what I cannot do here, which is what makes the balls indistinguishable, is that I said 2 are here because I'm only concerned with the quantity of balls inside the bin. My balls are completely pegged to the board. I cannot move these things around. If I could move these things around, it would cause trouble because then like, having these two versus having these two here will be different. But since I'm only concerned with the quantity, you can imagine these, stars as being pegged to the board. It can't move. And all I do is I just stick my first barrier corresponding to the amount inside my first bin. And that's why this counts the number of ways to put, that's why this counts the number of ways to put the 10 balls into 4 bins. The balls cannot move. The stars cannot move. And I simply just chop down a divider to tell you like how much is in the first one. Then I put a next one down, how much is in the second. Now, how many ways are there to do this? Notice here, there are still 10 stars and 4 minus 1 stripes. And why are there 4 minus 1 stripes? Because I only need 3 dividers to get 4 different regions. Now, how do I count this? If you look at this diagram here that I've drawn, all I need to do is shorten up these dividers. This is now a bit string. 10 zeros, 3 ones. How many ways are there to count this? Well, there are 13 total characters, and I choose 3 of them to be ones, the remainder is 0. 13 choose 3. I want to also give you some intuition about how to count this, the 13 choose 3. If you were to think about all of these 13 characters as being distinguishable, as if I labeled each of these 13 characters, that's 13 factorial. 13 factorial ways to order these characters around, if I could tell the difference between all of them. But what's the problem if I do 13 factorial? I've overcounted severely because these 10 zeros are indistinguishable. These 10 zeros, if I were to move this 0 and this 0, it'd be the same bit string. I shouldn't count it twice. So any movement of these zeros around, as long as they're still in the same positions, if I move the zeros around, it doesn't change my bit string. How many ways are there to move the zeros around and not change my bit string? 10 factorial. 10 factorial ways to move those zeros around. That's not all. If I don't move my zeros, I can still move my ones. How many ways are there to move my ones? 3 factorial. So for any given bit string, 10 factorial ways to move the zeros, 3 factorial ways to move the ones. So how many possible movements are there that preserve my bit string? 10 factorial times 3 factorial. So each bit string got counted 10 factorial times 3 factorial times when I assumed that I could tell the difference between all of the zeros and the ones. I know it's comfortable to think about things in terms of formulas, but another way I want to encourage you to think about a 13 choose 3 or an n choose m or an n choose k. N choose k, and I probably should have mentioned this before I did that, is the number of ways to pick a subset of k objects from a set of n objects. Instead of thinking about this in terms of the formula, think about it as a combinatorial object, which is the answer to this problem. Whenever you're presented with a problem of picking a subset of k objects from a set of n objects, the number of ways is n choose k. Think about it as like an auto answer to a problem of this form. How is that applied here? Well, I have 13 spaces. My set is my 13 spaces, and I need to pick a subset of 3 of them to put my ones down. My subset is where the ones go, is the positions of the ones. My big set is all 13 positions. My subset is the subset of positions where the ones go. I need to pick the number of ways to put the ones down, and that defines my bit string. So the total number of ways here is 13 possible positions. I pick a subset of 3 of them. Now, going back to my stars and stripes, can I generalize this? How many stars did I put down? Precisely the number of balls. But I also, so when I created this bit string, how many stars did I put down? Well, precisely the number of balls. How many stripes did I put down? One less than the number of bins. How many total positions were there in my bit string? Were there n zeros, m minus 1 ones, so total positions of n plus m minus 1 positions, from which I select the positions for the ones, and that defines my bit string. Equivalently, you could say it's n plus m minus 1, choose n. Because I have my n plus m minus 1 total positions, and I pick m minus 1 of them for the ones, and then that defines the bit string. Alternatively, I could pick where the zeros go. That also defines my bit string. So these two formulas are actually equivalent. Okay, because of time, can I try to get through everything and we can answer that after? Yeah. Right. Injective arrangement. Everyone can get at most one candy. So here's the key thing. Here, the candies are indistinguishable. So like all Jolly Ranchers, all the same flavor. But the bins are still distinguishable. It's all the same flavors of Jolly Ranchers. And you have a bunch of kindergarten students. Everyone can get at most one. But I mean, some might get none. Everyone can get at most one. How many ways are there to do that? Well, because the candies are indistinguishable. If I give this student, like, this candy and this student this candy, if I switch the two candies, that's not two different arrangements. The candies are the same. So all this injective part reduces down to is saying, if I have my n candies and my m students, if all the candies are the same, all I'm doing is picking who gets a candy, because nobody can get more than one candy. I'm just picking who can get a candy. From my m students, I am picking a subset of them to receive candy. How big is that subset? It's n students, because I have n candies. Notice how that matches exactly with this definition. What is the answer? From a set of m students, I pick n of them to receive the candy. All right, one more. So also for surjective arrangements. This doesn't quite count the surjective arrangements, because if I had 3 dividers, I could put, like 2 dividers in here. And this would not be a surjective arrangement. There are 2 ways to think about the formula for this for this entry here. One is more general, and one gives you the formula faster. Let's say again we do this 10 balls 4 bins thing. I give you the fast one first. Actually, no. Maybe I'll do the slower one first, and then the faster one. Slower one is to say, well, I have 4 bins, right? So how do I enforce that everyone gets at least one? I stick 1 into each bin first. And then I have balls and bins I can redistribute for the rest. So if I have 4, so the first way to do it is, okay, 1 ball in each bin. And then I can have free arrangements for the remaining 6 balls. So then that reduces down to, if I have surjective, I now have a 6-ball 4-bin problem. And this is a fairly general situation, because if you say, oh, how many, if I need at least two balls in each bin, then what do? Well, you stick 2 in each. How many remain? 2 remain. And then you have free arrangement for this 2. So then the free arrangement for this 2, you just back into here, just with a reduced number of balls. And I think this was practiced in the homework. The other way I want to give you, which is not quite as general as this, and so how would I derive this? Well, if I have at least 1 in each bin, so I have n, so I start out with like an n plus m minus 1 slots. But like, how many balls do we end up with? Well, this is simply n minus m, because I have to reduce the number of balls by putting 1 in each bin. I still have m bins, so I just plug it into this formula. The number of balls is n minus m. plus the number of bins is still m minus 1. Choose the number of bins, m minus 1. And so this n minus m plus m, these cancel, and I get n minus 1, choose m minus 1. The other way to think about this, imagine if you had these 10 stars here. Where are the only places I can put my barriers? I can't put a barrier here because that would mean the first one has nothing. I can't put a barrier here. That would mean the last one has nothing. Oh. The only spaces I can put barriers are here in these middle sections. And I can't put 2 barriers inside here because that means that one would have nothing. That means how many ways are there to do the surjective arrangement is I just need to pick a certain number of these slots in the middle to put down the barriers. How many available slots do I have? Well, it's one like in between each. So it's like, one after each except for the last one. So there are n minus 1 spaces to put for where I could put the barriers. How many barriers do I have to put down? Well, still m minus 1 as before. And so this gives you the number of ways for these surjective arrangements. Okay. The remaining 3, I'm going to start with the one down at the bottom right. Distinguishable balls, indistinguishable bins. So I can't tell. So this is the case where the candies are different, but I can't tell the difference between all the bins look the same to me. By definition, if you have distinguishable balls, indistinguishable bins, and everyone has to get at least one, that is the Stirling number, NM. Now I hope now I hope this intuition of saying, so what I did here when I did my n choose k was I gave you 2 interpretations. One is a formula, sort of like how to think about it formulaically. But the other thing I encourage you to do is think about this as a way of mapping this as an answer to a certain type of counting problem. As long as your counting problem takes this form, this automatically gives you this answer. And the reason I told you about this is because for a Stirling number nm, there is no actual clean formula like n choose k. Instead, if you want, so this whole idea of thinking about it formulaically, loses its power. But what you can still think of it as, but this way of thinking about the problem as mapping this as this, symbol as the answer to this problem still applies here. This symbol, Stirling number nm, maps to precisely the problem of distinguishable balls, indistinguishable bins. Everyone has to get at least one. How about for this? What if everyone doesn't have to get at least one? Well, then all you have to do is you have to split this up into cases for how many people can get. Like how many people get the candies. In this case, everyone has to get at least one candy. But how about what if I relax the restriction that everyone has to get at least one candy? Then I could have, for completeness, I could say one person gets all the candies, or 2, or 3, or 4, or for completeness, I could say 0, 1, 2, 3, all the way to everybody gets at least one candy. So I can write this as a sum, k equals 0 up to m, I believe, of n k. Let me check this. Yes. So what this index k is telling you is how many people will get candy. Once I know how many people will get candy, then I have Stirling number nk ways to give those k people candy. Why do I not have an m choose k to pick which k of the bins get candy? Because the bins are indistinguishable. It doesn't matter if I'm the first k, last k, any k in the middle. There's only one way to pick k bins from my m bins, because my bins are indistinguishable. If I pick k bins, it doesn't matter if I pick these k, these k, these k, all the same. Only one way to pick k bins from m indistinguishable bins. Once I have, and so if I want k people to get candy, I just take those k people and I have n Stirling number n k ways to give k people candy. Doesn't matter if it's these k people, these k people, these k people. So my bins are indistinguishable. I don't care which of the bins, which of the k bins actually contain candy. In effect, you can think about it as in like the bins are indistinguishable. They all look the same, and you can sort of like mix them up freely, and then you have the same arrangement. So it doesn't really matter if I pick the first k people to. I have n Stirling number nk to give the first k people, Stirling number nk to give the second, like last k people. It doesn't matter if it's first k or last k, because any mixing of my bins is the same arrangement. Last one is here. Surjective, I have n balls and m bins.
Yeah.
What this is I have, so this is not the complete expression yet. This is I'm saying everyone has to get at least one. Everyone has to get at least, so here I'm saying my balls are distinguishable, bins are distinguishable, and everyone has to get at least one. So all m people have to get at least one. All m people have to get at least one. All m people have to get at least one candy. So that gives me my n m. The key thing here is that the bins were indistinguishable. But in this case, the bins are distinguishable. So nm counts the number of ways. If I couldn't tell the difference, if I were completely blind to like the differences between the bins, I have nm ways of giving n candies to the m bins where everyone gets at least one. But now when I can tell the difference between the bins, you can think about this as saying you're the cafeteria worker, and so you can't tell the difference between the bins. You have n bins. You have nm ways, Stirling number nm ways to put your n candies into the m bins so that everyone gets at least one. Now the kindergarten teacher receives the bins. And so for each arrangement inside this nm arrangement, n candies inside your m bins, for each of those arrangements, the kindergarten teacher has m factorial ways to distribute that which bin to which student. And so this is how we go from like saying like, this is indistinguishable to distinguishable. All right, so that completes the chart for combinatorics. That's based, so the only one topic that I think that we should, that is missing is the principle of inclusion-exclusion. Anybody want me to cover that or? Okay, so can you have a show of hands? Okay, sure. All right, so I think this is best covered by an example. I'm going to show you the case for, three sets, but but the principle generalizes to more than one, more than three. Okay. Let's say I have three sets A, B, and C, and I want to count the number of total elements inside here. Now, if I were to just count the size of A plus the size of B plus the size of C, I would have overcounted. And why is that? If I count the size of A, I would have counted each of these things once, each of these things once, each of these things once. But this is a problem because I've now counted each of these things twice, and each of these things inside here 3 times. So how do I correct this? Well, I'm going to subtract off every combination of intersection. So A intersect B, I'm going to, uncount it once. A intersect C, I'm going to uncount it once. B intersect C, I'm going to uncount it once. That almost solves the problem. But now I don't have anything in here. So I just add back A intersect B intersect C. If you had more than 3 sets, The general way of thinking about it is the following. I'm going to do it for 4 because I think 4 is, less intuitive, but it generalizes to more than that. If I have 4 sets A, B, C, D, what you do first is you add up the sizes of the 4 sets. And so I'm going to draw it this way. Here, we're going to think about a sign. And here, we're going to write down the sizes of the sets. 4 sets here. Then in the next one, I'm going to write out every combination of 2 sets. A intersect B, A intersect C, A intersect D, every combination of 2 sets. B intersect C, B intersect D, C intersect D. Next one here. Every combination of 3 sets. A intersect B intersect C, A intersect B intersect D, and so on. Every combination of 4 sets, there should just be 1. And I'm going to start with a plus and alternate signs going down. What's my final answer? Plus this, plus this, plus this, plus this, minus, 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 plus, plus, minus. All right. And I want to give you a quick example. If I want to count, let's say, numbers from, say, 1 to up to, say, like 60. How many of them are multiples of 2 or 3 or 5? So again, I can construct this chart. In this case, there are 3 only. A, B, C. Every combination of 2 sets. A intersect B, B intersect C, A intersect C. Every combination of 3 sets. A intersect B intersect C. Now, how do I mark the signs? Start with plus. I always start with plus, and then I alternate down. And then what we have to do is just calculate the sizes of these 3 sets. Well, conveniently in this problem, we have, let A be the size of the set. How many are multiples of 2? B be the set. How many multiples of 3? B be the set of multiples of 3. C be the set of multiples of 5. How many are in A? Well, there are 30 of them. Because you could do 2, 4, 6, 8, all the way up to 60. How many in B? 20 of them. How many in C? 12. How many in A intersect B? So you have to be 2. You have to be a multiple of 2 and a multiple of 3. So there's multiples of 6. 10 of them. B intersects C, 3 and 5. So you have multiples of 15. 4 of them. A intersects C, multiples of 2 and 5. So multiples of 10. 6 of them. And how many A intersect B intersect C? So multiples of 2, 3, and 5, that's the same as multiples of 30, 2 of them. And so how many in total are multiples of 2 or multiples of 3 or multiples of 5? Well, 30 plus, so add all these, minus all these, plus this. So 30 plus 20 plus 12, this is 50, 62, 52, 48, 42, 44. And so the total number is 44. All right, so that's basically all I wanted to cover. I'm going to stop the recording, and I'll just stay after. I know I didn't answer questions for sort of the later parts, and I will try to post the recording as soon as possible. So good luck on your prelim. As a disclaimer, because of various other things happening this week, like exams and other commitments that so I won't be able to hold the office hours on Tuesday, and so sort of the only thing I think I'll proctor the exam on Thursday, but I won't be able to hold the office hour on Tuesday. And so, but in terms of Ed, if you have any questions for on the content, feel free to post them to Ed. The TAs, there are 60 TAs, so I mean it's pretty likely that somebody will be able to see it pretty promptly. Yeah, and so good luck on your prelim, and hope to see some of you on Thursday.